In this video, we're going to be solving an application problem using linear systems. So it's very possible that you might be asking yourself, well, how can I tell which application problems can be solved using a system of linear equations? Well, the answer comes from two conditions. One, does the problem involve more than one unknown quantity? And two, are there two or more equations or conditions to be satisfied? So when one or both of those conditions are met, the appropriate mathematical model for the problem may be a system of linear equations. Let's take a look at this problem. An airplane flying into a headwind travels 2,000 mile flying distance between Cleveland, Ohio and Fresno, California in 4 hours and 24 minutes. Now on the return flight, the airplane travels this distance in 4 hours. So we're going to find the airspeed of the plane and the speed of the wind, assuming that both remain constant. So we're going to let the airplane speed be our x, and we're going to let the speed of the wind be our y. So if we're traveling with a headwind, so we're going into the wind, right, into the wind, then that tells us that we're going to have to take the x value and we're going to need to subtract the y value, right? Because it's pushing against. Sorry, that's supposed to be the letter y. There we go. And so this is going to equal our speed of the plane against the wind. Right, so that's our headwind. Now on the return flight, though, we're able to travel that distance in just 4 hours. Okay, so it's on the return flight. So if on the way there we had a headwind, that means on the way back we're going to have a tailwind. So the wind is going to help push the plane, basically. So here we're going to have the x, and we're going to add that to our y value. And that's going to give us the speed of the plane with the wind. Right, so that's what we call a tailwind. And this first one was our headwind. So that's basically taking care of our rates, right? So those are rates. Now, in order to do this problem, we're going to use the distance formula, which is distance equals our rate times our time. Distance equals rate times time. So again, d equals our distance that we're flying, the r is our rate, and t is the amount of time that it takes. So as far as time goes, we're able to see that we have 4 hours and 24 minutes and 4 hours depending on which way we're traveling. All right, so let's go ahead and set this up. So we know that we're traveling 2,000 miles distance. Now our first rate is going to be the speed against the wind, with our headwind, right? So that's going to be our first rate, which is the x minus the y. And then times our time, right? So we're going to put the time with that. So our time here, oops, let's just fix that. So our time on this problem happens to be the 4 hours. Let's do that in green, right? Let's do that in green. So the 4 hours plus the 24 minutes out of 60 minutes, right? Okay. And then for our second one, we have a distance still of 2,000 because the distance between Cleveland, Ohio and Fresno, California did not change. It's the same distance. But this time we're traveling with our tailwind, which means that we had our x plus our y for our rate. And this time, our time is going to be just the 4 hours, right? Just the 4 hours. So we're going to go ahead and we're going to simplify our 4 plus 24 over 60. And so that's going to give us 2,000 equals x minus y times 22 over 5. And we'll just write our second equation because we're not really changing anything there. And so now we're going to distribute, right? We're going to distribute those. So this equation right here is going to become 2,000 equals 22 over 5x minus 22 over 5y. And then our second equation, we're going to distribute that 4, and we're going to get 2,000 equals 4x plus 4y. Now we want to see what can we do to turn 25 over 5 and 4, get them to have some common multiple. Like what does that make? Sometimes it can be pretty exhausting to try and find a number that will multiply and become both. And so when that happens, usually what I do is I just multiply one by the top and the other by each other, really. So I'm going to get rid of the x's to start. So, or actually the y's are kind of already set up for that. So I can do that by multiplying my top equation by 4 and my bottom equation by 22 over 5. Now when I say multiply, what I'm talking about is I'm going to be taking my 4 and I'm going to be multiplying it to all 3 of these pieces right there, right? That's going to multiply to all 3 of those. And when I do that, that's going to get me, let's give ourselves just a little bit more space here. That's going to get me 8,000 equals 88 over 5x minus 88 over 5y. Now I have to do the same thing with this 22 over 5. So it has to go to all 3 pieces. And so that is going to get me 8,000 equals 88 over 5x plus 88 over 5y. Then when I go to solve the system like you normally would, we're going to see that the y's are going to cancel out. And so what I'm going to end up having is we're going to end up having 16,000 equals 176 over 5x. So to solve this, we're going to go ahead and we are going to multiply by the reciprocal. So we're going to multiply by 5 over 176. So 5 over 176. So those will cancel out. And if I take 16,000 and I multiply that by 5 over 176, that's going to end up getting me 5,000 over 11 equals x. My mistake. I have a small little error back here in my math. Let's just erase this really quick. This is actually not 8,000. If I take 2,000 and I multiply that by 22 over 5, I actually end up getting 8,800. And that's going to make a pretty big difference. Just fix that. All right, so then when we add that, we get 16,800. All right, so if we take that 16,800 and we multiply that, we're going to get 5,250 over 11. And so we're talking about speed and miles. And so someone's like, wow, how fast do you think that car is going? You're not going to say, oh, 5,250 elevenths. That it doesn't really make sense. So what we really want to do is convert this, and we're going to say the x is going to be approximately 477.27 miles per hour. Right? So that's going to be the speed of our airplane. Because remember, the x was the speed of our airplane. And now we need to find y. So we're going to take that and we're going to kind of plug that in. So when I look at my equations and try to decide what should I plug it into, this equation looks like it's going to be the easiest equation and the nicest equation to plug that into. And so I'm going to go ahead and set that up, and I'm going to have my 2,000 equals, I know what x is. Let's just scoot this over a little bit. 4,777 and 22 plus our y value, which we don't know yet, and then times that by 4. All right, so in this particular instance, I am now going to divide both sides by 4 just to make that a whole lot smaller number-wise and a lot easier to deal with. And that's going to give me 500 equals 477.27 plus the y. And so to finish solving, we're just going to subtract the 477.27 from both sides, and we're going to find that our y value as far as speed goes for our aircraft is going to be, well, not really for the aircraft because that was our x, but the wind speed is going to be 22.73 miles per hour. And so we have our two answers. We have our airplane speed at 477.27 miles per hour and wind speed at 22.73 miles per hour. And so when our numbers are not very nice, we're still able to work through the problem, and systems really helps us to do that. So again, remember that in order to use, or how you can know if you're going to want to use a system of equations for like a real life problem is by asking yourself two questions. Does the problem involve more than one unknown quantity? And are there two or more equations or conditions to be satisfied? So if either of those or both of those are met, then the appropriate mathematical model to solve the problem is very highly likely a system of linear equations.